Hello, this is Jeffrey Fox. This MOOC gives some details of FutureGrid as a system and a project. It builds on an earlier MOOC called the Overview. It repeats some of those slides, takes a few and expands them, but it doesn't cover everything in that overview. But it does cover most things. There are also additional MOOCs on FutureGrid. One covers how to um, log into the portal and to get a project. Others cover core technologies such as Rain, Grizzly, Hadoop, and things like that. Have a great MOOC, and we'll get started on this one. Thank you. All right, so here's what we're going to cover today. We'll recap the overview MOOC. We'll give the hard one a little more detail than in the overview. We will describe some example FutureGrid projects, not repeating those described in the overview. We will give some details as one of the major projects, which is Exceed testing of FutureGrid. We'll describe the relation of FutureGrid to other projects in greater detail than in the overview. We'll discuss the future activities of FutureGrid in more detail and the security of FutureGrid in more detail. Then we move on to image generation, giving a little more detail on the timing measurements and the architecture for doing this. And again, this is followed by monitoring, where we'll give more details than before on monitoring. And finally, we'll discuss, as part of the education, how to use appliances or what appliances enable. First, the recap of the overview. So these slides are just a few of the overview, setting the scene for FutureGrid. This is an overview of FutureGrid, Testbed as a Service. FutureGrid is part of the NSF Exceeds system, which is a set of resources around the country. And unlike most of those resources, it is not a production system, but rather a testbed. And its focus is clouds, although it also supports HPC and grids, because you need all of those to build systems. And also comparison of clouds and HPC, for example, is an important capability that FutureGrid offers. We're now coming to the end of our third year of use, and we have one more year to go. The FutureGrid testbed provides to its users the support of research, and that research goes all the way from fundamental computer science through very applied applications, which is commonly called computational science. It provides a very flexible platform for both developing and testing systems and for looking at issues like interoperability, functionality, performance of software, and evaluating different technologies against each other. FutureGrid is customizable by the user at essentially all levels of the stack, is accessed interactively, and supports, as we said already, grid, cloud, and HPC software, and it can run with or without hypervisors, namely with or without virtual machines. A particular feature of FutureGrid is its rich education and teaching platform. It offers, with support, OpenStack, Eucalyptus, and Nimbus, three major open source virtual machine managers. It also runs OpenNebula and actually CloudStack, although those are not supported. They're used in some of the projects. And we support the use of MPI and other high-performance computing technologies. And this environment is currently allocated in a rather static fashion with discrete changes. We expect to be moving soon to a much more dynamic software-defined system approach where we can go back and forth between the different choices in a very flexible fashion. So this is the FutureGrid operating model. If you go to Amazon, you will get a bunch of virtual machines essentially, unless you take specialized services. But on FutureGrid, you can do almost anything. Namely, the model of FutureGrid is you pick an image, that image is loaded, that image can or cannot, can or does not have virtual machines, namely hypervisors, and you make that choice. So you can go back and forth between these different choices, and as I mentioned earlier, you can actually compare the overhead of hypervisors by running the same hardware with or without hypervisors. We have image libraries for a lot of the basic technologies, MPI, OpenMP, MapReduce. Dryad is actually now deprecated because Microsoft has stopped offering it, but there's Hadoop and Twister. Twister is an example of iterative MapReduce. We have the European G-Lite environment, Unicore, Globus. At the low level, we have Zen, KVM. We have ScaleMP on the cluster Echo. That's a distributed shared memory environment. And we support, as I've mentioned, Nimbus, Eucalyptus, OpenStack, OpenNebula. And we also have Windows, although that's not typically advertised, which you can use. And as mentioned, this can be done statically by pre-configured nodes or dynamically. And of course, as more users deposit more software in the library, the capability of FutureGrid grows. It is worth emphasizing that FutureGrid is small with only 4,700 distributed cores, and it has an almost dedicated network, which we'll find out when we look at the hardware in more detail. FutureGrid has a great set of partners. It is led by Indiana University, which has substantial hardware. The partners in red have hardware. It also is responsible for the architecture, the core software, and a lot of the support. San Diego has hardware, 2 clusters, Lima and Sierra, and its main focus is Inca and the monitoring and performance capabilities. University of Chicago and Argonne National Labs, they have the cluster hotel, and their focus is support of Nimbus. University of Florida is in charge of education and outreach, and has the virtual networking software Vine. It also develops many of the appliances. University of Southern California Information Sciences Institute, it works on Pegasus, and now enabling workflow on especially cloud systems. It also develops that workflow to manage experiments. I know workflow is well known from the grid research days, but workflow is critical for clouds because cloud supports software as a service, and workflow is precisely what you need to compose services to build a bigger system. Sometimes called a mashup in the more commodity arena. University of Tennessee Knoxville is responsible for benchmarking and getting PAPI to work on virtual machines. TAC, University of Texas Austin Advanced Computing Center, is responsible for Portal. It has a very significant machine, Alamo, and also some of the Exceed integration. The other Exceed integration site is University of Virginia, which also has a significant responsibility for the Open Grid Forum and its standards.